The per unit system. In power system, there are so many different elements such as motor loads, generators, transmission line, distribution lines, transformers, and all these components have different size and different nominal values. So to be able to compare the performance of the big and the small element, the per unit system is used. The per unit value of any quantity is defined as the actual value divided by the base value. Thus, the voltage, current, and impedance values are divided by the base values and expressed in per unit, or we can also express the value in percentage. For example, the percent impedance is equal to the actual impedance in ohm divided by the base impedance in ohm multiplied with 100%. Another example, in a synchronous generator with 13.8 kV as its nominal voltage, instead of saying the voltage is 12.42 kV, we say the voltage as 0.9 pu. So here 12.42 kV is the actual voltage and 13.8 kV is the nominal voltage or the base value. So we get the voltage in per unit as 12.42 kV divided by 13.8 kV, which is 0.9 pu. So how are the base values defined? For an electric element, we have power, voltage, current, and impedance. Usually, the nominal apparent power S and nominal voltage V are taken as the base values for power and voltage. So, using the apparent power and voltage as the base value, we can calculate the value for current and impedance. So, using the base power and base voltage, the base current can be computed as the base power divided by the base voltage. And the base impedance is equal to the base voltage divided by the base current, which is also equal to V base square divided by S base. For example, the per unit apparent power is equal to the actual apparent power divided by the base apparent power. The per unit current is equal to the actual current divided by the base current. The per unit voltage is equal to the actual voltage divided by the base voltage. And the per unit impedance is equal to the actual impedance divided by the base impedance. The conversion from per unit value to ohm and vice versa can also be obtained. For example, the per unit impedance is equal to the actual impedance divided by the base impedance, which is also equal to the base power divided by V base square multiplied with the actual impedance. And we can also calculate the actual impedance as the base impedance multiplied with the per unit impedance, which is also equal to the base voltage square divided by the base power multiplied with the per unit impedance. For transformer voltage base, so we have the primary side with the voltage V1 and the secondary side, which is the voltage is denoted as V2. So the voltage at the base voltage at primary side is V base 1 and the base voltage at the secondary side is V base 2. So the base voltage at secondary side is equal to voltage at secondary divided by voltage at primary multiplied with base voltage at the primary side. The per unit system in three-phase circuit, we concern about using phase or line voltage, and this can be removed in the per unit system. the actual values of the resistance, the reactance due to capacitance, the reactance due to inductance for the lines, cables, and other electrical equipment, typically in phase values. It is convenient to work in terms of the base VA or the base volt amperes. In three-phase system, usually the three-phase base apparent power or MVA base and line-to-line voltage V base or KV base are selected, and therefore we can calculate base current and the base impedance dependent on the base power and the base voltage. So we know that the base power is equal to SERT3 V base I base. So we can compute for the base current, which is equal to the base power divided by SERT3 V base. And we also know that the base voltage is equal to SERT3 I base multiplied with Z base. So that the base impedance is equal to V base divided by SERT3 divided by the base current, which is also equal to the base voltage square divided by the base power. If an impedance is expressed in a new base and an old base, we must have the old per unit impedance is equal to the actual impedance divided by the old base impedance, which is also equal to the old base power divided by the old base voltage square multiplied with the actual impedance. Expressing the actual impedance to a new power base and a new voltage base, thus we will get the new per unit impedance is equal to the actual impedance divided by the new base impedance, which is also equal to the new base power divided by the new base voltage square multiplied with the actual impedance. Okay, so this is number 1. This is equation number 2. From equation number 1 and equation number 2, the relationship between the old and the new per unit value can be obtained as the new per unit impedance is equal to the old per unit impedance multiplied with the new base power divided by the old base power multiplied with the old base voltage divided by the new base voltage square. If the voltage base are the same, so that we get this part is equal to 1, so 1 to the power of 2 is equal to 1, so we can eliminate this part. So we get the new per unit impedance is equal to the old per unit impedance multiplied with the new base power divided by the old base power. The steady state analysis using per unit approach, first is to select different regions or different zones according to the base voltage. And then number 2 is to pick the base power for the system. And then pick the base voltage according to the line-to-line voltage. Calculate the base impedance for different regions and zone. Express all quantities in per unit. Draw the impedance diagram and solve for per unit quantities and convert back to actual quantities if needed. The advantages of the per unit system, it gives us a clear idea of relative magnitude of various quantities such as voltage, current, power, and impedance. And the per unit impedance of equipment, the per unit impedance of equipments of the same general type based on their own rating fall in a narrow range regardless of the rating of the equipment, whereas their impedance in ohms vary greatly with the rating. The per unit values of impedance, voltage, and currents of transformer are the same regardless of whether they are referred to primary or in the secondary side. So this is the great advantage since the different voltage levels are disappear and the entire system reduced to its simple impedance diagram. And the per-unit system are ideal for the computerized analysis and simulation of complex power system problem.